Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into one of the most critical security vulnerabilities in AWS identity and access management, the confused deputy problem. This is a sophisticated privilege escalation attack that exploits the trust relationships between AWS services and accounts. Understanding this vulnerability is essential for any cloud security professional or AWS administrator, as it represents a fundamental weakness in how cross-account access is typically implemented. The confused deputy problem gets its name from a classic security scenario where a trusted intermediary is tricked into misusing its privileges. In the AWS context, the deputy is an AWS service or role that has been granted certain permissions. The confusion arises when an attacker can cause this deputy to perform actions on their behalf that the attacker shouldn't be able to perform directly. This isn't just a theoretical concern. It's a real-world attack vector that has been exploited in various forms across cloud environments. In this presentation, we'll explore exactly how the confused deputy attack works in AWS, why traditional IAM policies aren't sufficient to prevent it, and most importantly, how to properly remediate this vulnerability using AWS's recommended security controls. We'll look at real-world scenarios, examine the technical details of both the attack and defense mechanisms, and provide you with practical guidance to secure your AWS resources against this threat. Understanding the confused deputy problem. The confused deputy problem is fundamentally about identity confusion in a trusted relationship. Let me explain this with a clear scenario. Imagine you have an AWS account and you want to allow an external service provider to access certain resources in your account. The typical approach is to create an IAM role that the service provider can assume, and you grant that role the necessary permissions to access your resources. Here's where the vulnerability emerges. When you create this cross-account role, you specify a trust policy that says which external AWS account can assume this role. For example, you might say that account number can assume this role. However, here's the critical flaw. Anyone who has access to that external account can potentially assume the role. If an attacker gains access to the service provider's account, they can use the same role assumption mechanism to access your resources. The confusion happens because your IAM role trusts the external account, but it has no way to verify the actual identity of the principal trying to assume the role within that account. Your role becomes a confused deputy because it's performing actions on behalf of someone, but it can't distinguish between the legitimate service and an attacker who has compromised the service provider's account. This is particularly dangerous in scenarios where service providers manage resources for multiple customers, because a single compromise could potentially give an attacker access to all customer accounts. The attack vector becomes even more concerning when you consider that the service provider might use the same role assumption pattern for all their customers. An attacker who discovers this pattern in one customer environment can potentially apply the same technique to attack other customers. This creates a scalable attack vector where the cost of reconnaissance pays dividends across multiple targets. Attack scenario architecture. Let's examine the technical architecture of how a confused deputy attack actually unfolds in AWS. The attack involves multiple AWS accounts and exploits the trust relationship between them. We have three key players in this scenario: your AWS account, which contains sensitive resources, the service provider's legitimate AWS account that you trust, and the attacker who has somehow gained access to the service provider's account. The flow begins with your account creating a cross-account IAM role. This role has a trust policy that allows principals from the service provider's account to assume it. The trust policy contains the assume role action and specifies the service provider's account ID as the trusted principal. Critically, this trust policy doesn't include any additional conditions that would verify the specific identity of the caller beyond just the account ID. When the legitimate service operates, It assumes your role using the AWS Security Token Service Assume Role API call. The service authenticates to AWS using its own credentials from its account, and AWS validates that the requesting principal belongs to the trusted account ID. If validation succeeds, AWS issues temporary security credentials that include an access key ID, a secret access key, and a session token. These credentials inherit all the permissions attached to your cross-account role. Now here's where the attack happens. The attacker, having compromised something in the service provider's account, even a low-privilege IAM user or role, attempts the exact same Assume Role API call. AWS performs the same validation, checking only whether the requesting principal belongs to the trusted account. Since the attacker is operating from within the service provider's account, this validation passes. AWS has no way to distinguish between the legitimate service and the attacker because both are coming from the same trusted account. The attacker receives the same temporary credentials and gains access to your resources with whatever permissions the role grants. The diagram we're looking at illustrates this flow clearly. You can see your account on one side with the cross-account role, the service provider account in the middle with both the legitimate service and the attacker, and the flow of role assumptions and access. Notice how both the legitimate service and the attacker follow identical paths through the trust relationship, which is exactly why this attack is so effective and why additional security controls are necessary. Traditional trust policy limitations. Let's examine a traditional IAM role trust policy to understand exactly why it's vulnerable to the Confused Deputy attack. This is the type of trust policy that many organizations implement when setting up cross-account access, and it represents the baseline configuration that leaves you exposed to this vulnerability. The trust policy is a JSON document that defines who can assume the IAM role. At the top level, we have the version field which specifies the policy language version, typically set to 2012-10-17. The statement array contains one or more permission statements that define the trust relationships. Each statement is evaluated by AWS when someone attempts to assume the role. The effect field specifies whether to allow or deny the action. In trust policies, this is almost always set to allow because you're explicitly granting permission to assume the role. The principal field is critical because it defines who is allowed to assume the role. In a cross-account scenario, this contains an AWS key with the value being the account ID of the trusted external account. This is where the fundamental weakness lies. The policy trusts the entire external account, not a specific principal within that account. The action field specifies what action is being permitted. For role assumption, this is always STS:\assume role, which refers to the security token service Assume Role API operation. This is the API call that principals use to obtain temporary security credentials for the role. The critical problem with this trust policy structure is that it lacks any condition block. The condition block is where you can add additional constraints to further restrict who can assume the role beyond just the account ID. Without conditions, any principal in the trusted account who has STS:\assume role permissions on their own side can assume this role. This includes not just the intended service, but any IAM user, any IAM role, even Lambda functions or EC2 instances running in that account if they have the necessary permissions. When an attacker compromises any resource in the service provider's account, even a low-privilege one, they can potentially escalate their privileges by assuming roles in customer accounts that trust the service provider. The trust policy we're examining has no mechanism to verify the specific identity or to ensure that only the legitimate service is making the assumption request. This is precisely what makes it vulnerable to the Confused Deputy attack. The External ID solution. AWS provides a specific security feature designed to prevent the Confused Deputy problem, and that feature is called the External ID. The External ID is a unique identifier that you share with the third-party service provider, and it must be included in the role assumption request. This creates a shared secret between you and the legitimate service that an attacker would not possess even if they compromise other parts of the service provider's account. The concept is elegantly simple, yet highly effective. When you create the cross-account role, you generate a unique, random external ID value. This value should be cryptographically random and unguessable, typically a UUID or a long random string. You then configure this external ID in two places. First, in your IAM roles trust policy as a condition that must be satisfied, and second, you provide this same value to the legitimate service provider through their configuration interface. When the legitimate service needs to assume your role, it includes this external ID as a parameter in the Assume Role API call. AWS then evaluates the trust policy and checks whether the provided external ID matches the value specified in the condition block. If the values match, the assumption proceeds. If they don't match or if no external ID is provided when one is required, the assumption fails and AWS returns an access denied error. The security value of the external ID comes from the fact that it's a secret known only to you and the legitimate service. An attacker who compromises the service provider's account would not automatically know the external ID values that different customers have configured. Even if the attacker can assume some roles in other accounts that don't use external IDs, they cannot assume roles in accounts that properly implement this control. The external ID essentially acts as a password that proves the caller is the intended service and not just any principal from the trusted account. It's important to understand that the external ID doesn't replace the account trust in the principal field, it augments it. You still specify the service provider's account ID in the principal field, because you want to ensure the request comes from that specific account. The external ID adds an additional layer of verification on top of the account verification. Both conditions must be satisfied for the role assumption to succeed. The request must come from the correct account and it must include the correct external ID. Implementing external ID in trust policy. Now let's look at the actual implementation of the external ID in an IAM role trust policy. This is how you properly secure a cross-account role against the confused deputy attack. The structure is similar to the traditional trust policy we examined earlier, but with a crucial addition, the condition block. The trust policy still begins with the version field set to 2012-10-17. The statement array still contains the permission statement that defines the trust relationship. The effect is still allow. The principal still specifies the trusted account ID using the AWS key, and the action is still sts:\assume role. All of these elements remain the same because they serve their original purpose of establishing the basic trust relationship with the external account. The key difference is the condition block that we have added to the statement. The condition block allows you to specify additional requirements that must be met for the statement to take effect. In this case, we are using the string equals condition operator, which performs a case-sensitive string comparison. This operator is appropriate for external ID because we want an exact match with no flexibility. Inside the string equals condition, we specify the condition key sts:\external ID. This is a special condition key that AWS recognizes when evaluating assume role requests. The value of this condition key is set to the unique external ID that you've generated for this particular service provider. In the example shown, we're using a UUID format, but any sufficiently random string would work. The important thing is that it's unique to this relationship and not easily guessable. When a principal attempts to assume this role, AWS evaluates the trust policy in this sequence. First, it checks whether the requesting principal belongs to the account specified in the principal field. If this check fails, the request is immediately denied. If it passes, AWS then evaluates the condition block. It looks at the external ID parameter that was provided in the Assume Role API call, and compares it to the value specified in the sts:\external ID condition. Only if both the account check and the external ID check pass does AWS allow the assumption and issue temporary credentials. This implementation effectively prevents the confused deputy attack because an attacker, even one operating from within the trusted account, cannot satisfy the external ID condition without knowing the secret value. The legitimate service knows this value because you've configured it through their interface. The attacker does not have access to your configuration with the service provider, so they cannot obtain the external ID. Their assumption attempts will fail at the condition evaluation stage, preventing them from accessing your resources. External ID workflow and verification. Understanding the complete workflow of how external ID protects against attacks requires examining the step-by-step process that occurs when roles are assumed, both by legitimate services and by potential attackers. This workflow demonstrates exactly why the external ID mechanism is effective at preventing the confused deputy problem. The workflow begins with the setup phase in your AWS account. You create the cross-account IAM role with a trust policy that includes the condition block requiring a specific external ID. You generate a strong, random external ID value. This could be a UUID, a long random alphanumeric string, or any other unpredictable value. You then configure this external ID with the service provider through their administrative interface. The service provider stores this value in their system associated with your customer account. When the legitimate service needs to access your AWS resources, it retrieves the external ID that you configured during setup from its internal database or configuration system. It then makes an assume role API call to AWS Security Token Service, providing three key parameters: the ARN of the role to assume, which uniquely identifies your cross-account role, an optional role session name which is a label for the session, and critically, the external ID parameter containing the value you configured. AWS receives this request and begins the validation process. First, it verifies that the requesting principal belongs to the account specified in the role's trust policy principal field. This is the standard cross-account verification that happens with or without external ID. Assuming this check passes, AWS then evaluates the condition block. It extracts the external ID parameter from the API request and compares it to the value specified in the STS:*external ID condition using the string equals operator. If the values match exactly, both validation steps have passed, and AWS issues temporary security credentials to the legitimate service. Now let's contrast this with an attack scenario. An attacker who has compromised something in the service provider's account attempts to assume your role. The attacker discovers your role ARN, perhaps through configuration files, logs, or by scanning for accessible roles. The attacker makes an assume role API call, but here's the critical point. The attacker doesn't know your external ID because it's not stored in any location the attacker can access. The attacker might try the request without an external ID, or they might try to guess the value, but cryptographically random UUIDs are essentially impossible to guess. AWS receives the attacker's request and performs the same validation sequence. The account verification passes because the attacker is indeed operating from within the trusted account. However, when AWS evaluates the condition block, the comparison fails. Either the attacker provided no external ID and the condition expects one, or the attacker provided an incorrect value. Either way, the string equals condition is not satisfied. AWS denies the request and returns an access denied error to the attacker. The attacker cannot access your resources despite having successfully compromised the trusted account. Best practices for external ID implementation. While the external ID mechanism is straightforward in concept, proper implementation requires following several important best practices to ensure maximum security. These practices address common pitfalls and ensure that your protection against the confused deputy problem is robust and maintainable. First and foremost, uniqueness is critical. Every external ID must be unique per service provider and ideally unique per customer relationship if you're a service provider. Never reuse external IDs across different roles or different service providers. Each cross-account relationship should have its own distinct external ID. This practice limits the blast radius if an external ID is ever compromised. An attacker who learns one external ID can only assume that specific role, not roles in other accounts or for other services. The randomness and unpredictability of the external ID is equally important. Use cryptographically secure random number generators to create external IDs. UUIDs version 4 are excellent choices because they're standardized, widely supported, and provide sufficient entropy to be practically unguessable. Avoid using predictable patterns, sequential numbers, or values derived from other identifiable information like account IDs or customer names. An attacker who can predict or derive your external ID defeats the entire purpose of the mechanism. Length matters for security. While AWS doesn't enforce a minimum length for external IDs, best practice is to use values that are at least 32 characters long. Longer values provide more entropy and make brute force attacks completely infeasible. However, don't make them so long that they create practical problems. AWS supports external IDs up to 1,224 characters, but values in the range of 32 to 128 characters provide excellent security while remaining manageable. Secure storage and transmission of external IDs is critical. Treat external IDs as sensitive secrets similar to passwords or API keys. When you share the external ID with the service provider, use secure channels like encrypted email, secure web forms, or API calls over HTTP pages. Never transmit external IDs through unencrypted channels or store them in publicly accessible locations. In your own systems, store external IDs in secure configuration management systems or secret managers like AWS Secrets Manager or Parameter Store with encryption enabled. Documentation and rotation policies are often overlooked but important aspects. Document which external ID corresponds to which service relationship in your security documentation. This helps during incident response and security audits. Consider implementing a rotation policy for external IDs, especially for high security environments. While rotating external IDs is more complex than rotating regular credentials because it requires coordination with the service provider, periodic rotation adds an additional layer of security and limits the window of exposure if a value is ever compromised. Monitoring and auditing should include external ID usage. Enable AWS CloudTrail logging for assume role API calls and periodically review these logs. Look for failed assumption attempts that might indicate an attacker trying to assume roles without the correct external ID. Successful assumptions should also be monitored to ensure they align with expected usage patterns. Unusual patterns might indicate that an external ID has been compromised. External ID and assume role API call. Let's examine the actual AWS command line interface command that demonstrates how the external ID is used when assuming a role. This is the practical implementation that the legitimate service provider would execute when accessing your AWS resources. Understanding this command helps you verify that services are correctly implementing the external ID mechanism and helps you test your own implementations. The command uses the AWS command line interface, specifically the STS service, which is AWS Security Token Service. The assume role operation is the API call that requests temporary security credentials for a specified role. This is the fundamental operation that enables cross-account access in AWS. The first parameter is role ARN, which specifies the Amazon resource name of the role to assume. The ARN uniquely identifies the role and includes several components. It starts with ARN:AWS:IAM:, followed by your account ID, then /role/ and finally the name of the role. In this example, the account ID is 1234567890, and the role name is third-party access role. This is the role you created in your account with the trust policy that requires the external ID. The role session name parameter provides a name for the temporary session that will be created. This name appears in CloudTrail logs and can be useful for auditing and tracking which service instances or processes are assuming the role. It's a string that you can set to anything meaningful. In this example, it's set to service session 1. Choose descriptive session names that help you identify the source of API calls in your logs. The critically important parameter is external ID. This is where the service provider includes the unique external ID value that you configured with them. In this example, the external ID is a UUID 12345678 ABCD 1234 ABCD 1234567890. This is the shared secret that proves the caller is the legitimate service and not an attacker. When AWS evaluates the trust policy of the role, it will compare this value to the STS:(external ID condition in the policy. When this command executes successfully, AWS returns a JSON response containing temporary security credentials. This response includes an access key ID, a secret access key, and a session token. These three values together form a complete set of temporary credentials that the service can use to make API calls to AWS with the permissions granted to the role. The credentials are time-limited, typically valid for 1 hour by default, though this duration can be configured. If the command fails, which would happen if an attacker tried to execute it without the correct external ID, AWS returns an error. The error message would indicate that the request was denied, and CloudTrail would log the failed assumption attempt. This is why monitoring failed assume role attempts is an important security practice. A pattern of failures might indicate an attack in progress. Additional security controls and defense in depth. While the external ID is the primary defense against the confused deputy problem, a comprehensive security strategy employs multiple layers of protection. Defense in depth is a fundamental security principle that ensures no single point of failure can compromise your system. Let's explore the additional controls you should implement alongside external ID to create a robust security posture for cross-account access. The principle of least privilege should guide all permission assignments to cross-account roles. Just because a service needs access to your account doesn't mean it needs broad permissions. Carefully analyze what specific actions the service actually needs to perform and grant only those permissions. For example, if a backup service only needs to read S3 objects, grant S3 get object permission for specific buckets rather than broad S3 permissions or admin-level access. Every permission you grant is a potential attack surface if the role is compromised. Resource-based policies provide an additional layer of access control directly on AWS resources. Services like S3, SQS, SNS, and Lambda support resource policies that can restrict access even if a principal has IAM permissions. You can configure these policies to require specific conditions such as the source account, source ARN, or other context. This creates defense in depth because even if an attacker assumes your cross-account role, they still face additional authorization checks at the resource level. Service control policies in AWS organizations offer a powerful way to set guardrails across your entire organization. SCPs can prevent certain actions even if IAM policies would otherwise allow them. For example, you could create an SCP that prevents deletion of critical resources or restricts access to sensitive services. SCPs apply to all principals in an account, including assumed roles, providing an additional security boundary that operates independently of role permissions. Condition keys in IAM policies allow you to restrict access based on request context beyond just the external ID. You can require that API calls come from specific IP address ranges using the AWS:/source IP condition, or you can require multi-factor authentication using AWS:/multi-factor auth present. You can restrict the time of day when access is allowed using date and time condition operators. You can even require that calls are made through specific VPC's endpoints using AWS:/source VPC. Each additional condition narrows the attack surface. CloudTrail logging and monitoring form the detection component of your security strategy. Enable CloudTrail in all regions and configure it to log to a dedicated security account that the cross-account roles cannot access. Monitor for unusual patterns in role assumption, such as assumptions from unexpected IP addresses, failed assumption attempts that might indicate reconnaissance, or successful assumptions followed by unusual API activity. Set up CloudWatch alarms and AWS Guard Duty to alert you to suspicious behavior in real time. Regular security audits and access reviews are essential maintenance activities. Periodically review which cross-account roles exist, which external accounts they trust, and what permissions they grant. Verify that external IDs are still unique and properly configured. Check whether services are still actively using the roles or if some can be deleted. Use AWS IAM Access Analyzer to identify any roles that grant access to external principals and verify that this access is still necessary and properly secured. Service Control Policies for additional protection. Service Control Policies, or SCPs, are a powerful governance tool available in AWS organizations that provide an additional layer of protection against the confused deputy problem and many other security threats. SCPs operate at the organization or organizational unit level and can enforce boundaries that apply to all principals in an account, including IAM users, IAM roles, and even assumed cross-account roles. This makes them an excellent complement to the external ID mechanism. The fundamental principle of SCPs is that they define the maximum permissions available to principals in an account. Even if an IAM policy grants a permission, an SCP can block that permission from being used. SCPs and IAM policies work together through an implicit deny model. A principal can only perform an action if both the SCP allows it and the IAM policy allows it. If either denies the action or simply doesn't allow it, the action is blocked. This creates a powerful guardrail system where organization administrators can prevent certain dangerous operations regardless of what individual account administrators configure. In the context of the confused deputy problem, security control policies, or SCPs, can be used to enforce security requirements on cross-account roles. For example, you could create an SCP that prevents the deletion of critical resources, like CloudTrail trails, or prevents the modification of key security configurations. Even if an attacker successfully assumes a cross-account role through a confused deputy attack, the SCP would prevent them from performing the most damaging actions. This significantly reduces the impact of a successful attack. Another powerful use of SCPs is to deny operations that don't meet specific conditions. You could create an SCP that requires all assume role operations to include an external ID condition in the role's trust policy. This would prevent account administrators from creating vulnerable roles even if they don't fully understand the confused deputy problem. The SCP acts as an automated policy enforcement mechanism that catches misconfigurations before they can be exploited. SCPs can also restrict access based on request context. You can create SCPs that deny actions unless they come from specific IP address ranges, require MFA authentication, or occur during specific time windows. These conditions apply to all principals in the account, including assumed roles. If an attacker assumes a cross-account role but tries to use it from an unexpected location or without MFA, the SCP blocks the action even though the role assumption itself succeeded. It's important to understand the relationship between SCPs and IAM policies. SCPs do not grant permissions, they only limit them. You still need IAM policies to actually grant permissions to perform actions. Think of SCPs as drawing boundaries around what's possible in an account, while IAM policies determine what specific principals can do within those boundaries. This separation of concerns is valuable because it allows central security teams to enforce organization-wide policies while still giving account administrators flexibility within those constraints. CloudTrail monitoring for confused deputy attacks. AWS CloudTrail is your primary tool for detecting potential confused deputy attacks and investigating security incidents related to cross-account access. CloudTrail records all API calls made in your AWS account, including assume role operations, and provides detailed information about who made the request, when they made it, where they made it from, and what parameters they included. This data is invaluable for security monitoring and forensic analysis. When monitoring for confused deputy attacks, you should focus on several key CloudTrail event types. The most important is the assume role event, which is generated whenever any principal attempts to assume an IAM role. This event contains critical fields including the user ID entity, which shows who made the request, the source IP address showing where the request came from, the request parameters showing what role was being assumed and whether an external ID was provided, and the response elements showing whether the assumption succeeded or failed. Failed assume role attempts are particularly interesting from a security perspective. A pattern of failed assumption attempts against your cross-account roles could indicate an attacker attempting to assume roles without the correct external ID. The failures occur because the attacker doesn't know the external ID value, so AWS denies their requests when the condition evaluation fails. If you see multiple failed assumptions from unexpected IP addresses or at unusual times, this is a strong indicator of malicious activity. Even successful assume role events should be monitored for anomalies. You should establish a baseline of normal behavior for your cross-account roles. What IP addresses typically assume them, at what times of day, how frequently, and what actions are performed after assumption. Deviations from this baseline might indicate a compromised external ID or legitimate service operating abnormally. For example, if a role that's normally assumed once per day suddenly gets assumed hundreds of times, or if it's assumed from a geographic region where the service provider doesn't operate, these are red flags. The user agent field in CloudTrail events can also provide valuable information. This field shows what software made the API request. Legitimate services typically use consistent user agents that identify their software and version. An attacker using the AWS command line interface or SDK might have a different user agent pattern. While sophisticated attackers can spoof user agents, many don't, making this a useful detection signal when combined with other indicators. CloudTrail events also include a shared event ID when requests are made using temporary credentials from assumed roles. This allows you to correlate the assume role event with subsequent actions performed using those credentials. You can trace the entire chain of activity from role assumption through resource access to understand exactly what was done during a session. This is crucial for incident response and forensic analysis when investigating suspected confused deputy attacks. Setting up CloudWatch alarms for detection. While CloudTrail logs all the data you need to detect confused deputy attacks, manually reviewing logs is not practical for real-time security monitoring. CloudWatch alarms integrated with CloudTrail provide automated detection of suspicious patterns. By creating metric filters that identify concerning events and alarms that notify you when thresholds are exceeded, you can achieve near real-time detection of potential attacks. The process begins with creating a CloudWatch logs metric filter on your CloudTrail log group. A metric filter scans log entries and increments a custom CloudWatch metric when specific patterns are detected. For confused deputy detection, you want to create filters that match failed assume role attempts. The filter pattern searches for CloudTrail events where the event name is assume role and the error code indicates an access denied or similar failure. Once the metric filter is creating data points for failed assumptions, you create a CloudWatch alarm on that metric. The alarm defines a threshold that determines when you should be notified. For example, you might set the alarm to trigger if there are more than 5 failed assume role attempts within a 5-minute period. This threshold should be tuned based on your environment: too sensitive and you'll get false alarms from legitimate errors, too lenient and you might miss attacks. When the alarm enters the ALARM state because the threshold has been exceeded, it can trigger various actions through Amazon's simple notification service. You can configure simple notification service to send email notifications to your security team, send messages to Slack or other chat platforms, invoke a Lambda function to perform automated response actions, or integrate with incident management systems like PagerDuty. The key is to ensure that alarms result in timely human review or automated investigation. Beyond just failed assumptions, you should also create alarms for successful assumptions that exhibit unusual patterns. This requires more sophisticated metric filters that can identify anomalies. For example, you could create a metric that counts assume role events from IP addresses that aren't in your known service provider IP ranges. An alarm on this metric would alert you when roles are being assumed from unexpected locations, which could indicate a compromised external ID or a sophisticated attacker who successfully obtained the secret. Another valuable alarm monitors the rate of successful assumptions. If a role that's typically assumed a few times per day suddenly gets assumed hundreds of times in an hour, this could indicate automated abuse by an attacker who has gained access. Rate-based alarms help you detect this type of anomalous behavior even when individual events appear legitimate. The alarm configuration should include appropriate notification channels and response procedures. Your security team needs clear documentation about what each alarm means and what actions to take when it fires. False positives should be investigated and used to tune the alarm thresholds. True positives require immediate incident response procedures, including potentially disabling the compromised role, rotating external IDs, and investigating what resources were accessed during the attack. AWS Config Rules for Compliance Verification. AWS Config is a service that continuously monitors and records your AWS resource configurations and allows you to automate the evaluation of configurations against desired settings. For preventing confused deputy attacks, AWS Config Rules can automatically verify that all cross-account IAM roles are properly configured with external ID requirements. This provides ongoing compliance verification rather than one-time checks. AWS Config works by recording configuration snapshots of your resources at regular intervals and whenever changes occur. For IAM roles, it captures the complete role definition including the trust policy, attached policies, and metadata. This historical record allows you to see how roles have changed over time and identify when potentially vulnerable configurations were introduced. Config rules are automated compliance checks that evaluate resource configurations against defined criteria. AWS provides some managed config rules, but for confused deputy prevention, you'll likely need to create a custom rule. A custom config rule uses an AWS Lambda function to evaluate resources and determine whether they comply with your security requirements. The Lambda function for a confused deputy config rule would retrieve all IAM roles in the account and examine their trust policies. For each role that trusts an external AWS account, the function checks whether the trust policy includes a condition block requiring an external ID. If a role trusts an external account but lacks the external ID condition, the function marks it as non-compliant. The function can also verify that external IDs meet minimum length requirements or follow expected patterns like UUID format. When config rules detect non-compliant resources, they can trigger various remediation actions. The simplest is sending notifications through SNS to alert security teams that a vulnerable role exists. More advanced setups can use AWS Systems Manager automation or custom Lambda functions to automatically remediate the issue by adding an external ID requirement to the trust policy. However, automatic remediation must be implemented carefully because it could break legitimate service integrations if not coordinated properly. Config also provides a compliance dashboard that shows the overall compliance status of your account. You can see at a glance how many IAM roles are compliant versus non-compliant with your external ID requirements. This visibility is valuable for security reporting and for tracking improvement over time as you remediate vulnerable configurations. The combination of config rules with service control policies provides comprehensive prevention. SCPs prevent new vulnerable roles from being created by denying role creation or modification that doesn't include external ID conditions. Config rules detect any existing vulnerable roles that were created before the SCP was in place. Together, they ensure both that new vulnerabilities aren't introduced and that old vulnerabilities are identified and remediated. IAM Access Analyzer for Cross-Account Access Review. IAM Access Analyzer is an AWS service specifically designed to help you identify resources in your account that are shared with external entities. It continuously monitors your resources and alerts you when it finds resources that grant access to AWS accounts, IAM principals, or organizations outside your zone of trust. This makes it an excellent tool for discovering potential confused deputy vulnerabilities and for maintaining visibility into your cross-account access patterns. Access Analyzer works by analyzing resource-based policies and IAM role trust policies to identify external access. When you create an analyzer, you define your zone of trust, which is typically your AWS organization or a specific set of AWS accounts that you control. The analyzer then examines policies and flags any access grants to principals outside this zone. For IAM roles, it specifically looks at trust policies to identify roles that can be assumed by external accounts. When Access Analyzer finds a cross-account role, it generates a finding that provides detailed information about the access. The finding includes the resource ARN showing exactly which role is affected, the principal who has access which shows the external AWS account or specific principals, the access level categorizing what type of permissions are granted, and the condition analysis showing what conditions, if any, are required for the access. This last field is particularly relevant for confused deputy detection because it tells you whether an external ID or other conditions are protecting the role. The condition analysis in Access Analyzer findings is sophisticated. It doesn't just show that a condition exists, it evaluates whether the condition actually restricts access in a meaningful way. For example, if a trust policy includes a condition block but the condition is always true or is trivially satisfiable, Access Analyzer might flag this as not providing real protection. This helps you identify cases where developers might have added a condition thinking it provides security when it actually doesn't. Access Analyzer can also help you discover unexpected cross-account access. Sometimes roles are created during development or testing with overly permissive trust policies, and they're forgotten when the temporary work is complete. Access Analyzer surfaces these configurations by continuously scanning your account. Regular review of Access Analyzer findings should be part of your security operations to ensure you know about all external access and can verify that it's properly protected. The service integrates well with other AWS security tools. Access Analyzer findings can be sent to Security Hub for centralized security management, exported to CloudWatch events for automated processing, or retrieved via API for integration with your own security tools. You can use these integrations to build automated workflows that verify external ID protection or alert security teams when new cross-account access is detected. One particularly useful feature is the ability to archive findings that you've reviewed and determined are acceptable. When you archive a finding, Access Analyzer stops alerting you about that specific access configuration unless it changes. This allows you to focus on new or modified access patterns rather than being overwhelmed by alerts about known and approved cross-account relationships. However, you should periodically review archived findings to ensure they still represent legitimate and properly secured access. Incident response for suspected confused deputy attacks. Despite all preventive measures, you must be prepared to respond effectively if you detect or suspect a confused deputy attack in your AWS environment. A well-planned incident response process can minimize damage and help you quickly contain and remediate the threat. The response process should be documented in advance and regularly practiced through tabletop exercises or simulations. The first phase is detection and initial assessment. This typically begins when one of your monitoring systems alerts you to suspicious activity, such as a CloudWatch alarm triggering on failed assume role attempts, an access analyzer finding showing unexpected cross-account access, or anomalous behavior detected by guard duty. Your first action should be to preserve evidence by ensuring CloudTrail logs are being captured and protected from deletion. Then perform initial triage to determine the severity and scope of the potential incident. The containment phase focuses on stopping the attack and preventing further damage. The most immediate action is to disable or delete the affected cross-account role to prevent any further assumptions. However, this must be done carefully because it will also break legitimate service access. If possible, modify the trust policy to add a condition that will block the attacker but allow legitimate access, such as restricting assumptions to specific source IP addresses if you know the service provider's IP ranges. Alternatively, you could rotate the external ID by updating it in the trust policy and notifying the legitimate service provider of the new value. During containment, you should also enable additional logging and monitoring. Increase the retention period for CloudTrail logs if needed. Enable detailed API logging for resources that the assumed role can access, and set up real-time monitoring for any continued suspicious activity. These measures help you track whether the containment actions were effective and provide more data for the investigation phase. The investigation phase aims to understand what happened, how the attack occurred, and what data or resources were accessed. Review CloudTrail logs to identify all assumed role events for the affected role, both successful and failed attempts. For successful assumptions, trace the subsequent API calls made using the temporary credentials to see what resources were accessed, what data was read or modified, and what configurations were changed. Look at the source IP addresses to determine where the attacker was operating from and examine the timeline to understand when the attack began. The recovery phase involves restoring normal operations and remediating any damage. If the attacker modified configurations, restore them from backups or known good states. If data was exfiltrated, determine what data was accessed and assess the impact according to your data classification policies. Update the external ID for the affected role and coordinate with the service provider to update their configuration. Test that legitimate service access is working properly before considering the incident resolved. The final phase is post-incident review and lessons learned. Document what happened, how it was detected, how long it took to respond, and what the impact was. Identify any gaps in your security controls that allowed the attack or delayed detection. Update your incident response procedures based on what you learned. Consider whether you need to implement additional preventive controls, improve monitoring, or enhance your security awareness training. Share lessons learned with relevant stakeholders to prevent similar incidents in the future. Real-world example. S3 bucket access scenario. Let's examine a concrete real-world scenario that illustrates the confused deputy problem and its remediation in the context of Amazon Simple Storage Service bucket access. This is a common pattern where many organizations have been vulnerable, making it an instructive example. The scenario involves a third-party backup service that needs to access your Amazon Simple Storage Service buckets to perform automated backups of your data. In the vulnerable configuration, you create an IAM role called Backup Service Role that grants S3 Get Object, S3 Put Object, and S3 List bucket permissions on your backup buckets. The trust policy for this role allows the backup service's AWS account to assume the role. You provide the role ARN to the backup service through their web portal, and they begin backing up your data. Everything appears to work correctly, but you've created a confused deputy vulnerability. The attack scenario unfolds when a malicious actor compromises an IAM user account in the backup service's AWS environment. This could happen through phishing, credential stuffing, or exploitation of a vulnerability in the backup service's infrastructure. The compromised account might have limited permissions in the backup service's own account, but the attacker discovers that they can assume customer roles. They scan for accessible roles and discover your backup service role. The attacker uses the AWS command line interface to assume your backup service role, providing the role ARN they discovered. Because your trust policy only checks the account ID and the attacker is operating from within that account, AWS grants them temporary credentials. The attacker now has access to all your S3 buckets that the role can access. They can list bucket contents, download sensitive data, upload malicious files, or delete existing backups. The attack goes undetected if you're not monitoring for unusual role assumptions or data access patterns. The proper remediation involves implementing an external ID requirement. You generate a unique external ID. Let's say it's a universally unique identifier like 9A7B3C2D-1E4F-5A6B-8C9D-0E1F2A3B4C5D. You update the backup service role trust policy to include a condition block requiring this specific external ID value. You then log into the backup services portal and enter this external ID in their configuration settings for your account. The backup service stores this value and includes it in all assume role requests. Now, when the legitimate backup service needs to access your S3 buckets, it retrieves your external ID from its database and includes it in the assume role API call. AWS validates both the account ID and the external ID, and because both match, the service successfully assumes the role and can perform backups. However, when the attacker who compromised the backup services account tries to assume the role, they don't have access to your external ID because it's stored securely in the backup services customer database, which the compromised account cannot access. The attacker's assume role attempt fails, and AWS denies access. This example demonstrates several important points. First, the vulnerability exists even when working with reputable service providers because any account can potentially be compromised. Second, the fix is straightforward and doesn't disrupt legitimate operations when implemented correctly. Third, the external ID provides strong protection because it's a shared secret that attackers cannot easily obtain even when they compromise parts of the service provider's infrastructure. This pattern applies to any scenario where you grant cross-account access to third-party services. Lambda execution role cross-account scenario. Another common real-world scenario involves AWS Lambda functions that need to access resources in other AWS accounts. This pattern is frequently used in multi-account architectures where centralized services in one account need to perform operations in workload accounts. The confused deputy problem can arise in these scenarios if not properly secured with external IDs. Consider a scenario where you have a centralized monitoring account that runs Lambda functions to collect metrics and logs from multiple workload accounts. Each workload account creates a cross-account role that allows the monitoring account to assume it and read CloudWatch metrics and logs. The typical implementation creates a role with a trust policy that simply trusts the monitoring account's root principal, allowing any principal in that account to assume the role. The vulnerability emerges because the monitoring account might host multiple services and have multiple developers with access. If an IAM user in the monitoring account gets compromised, or if a developer accidentally or maliciously uses their credentials inappropriately, they can assume the cross-account roles in all workload accounts. This is a classic confused deputy scenario where the workload accounts trust the monitoring account, but any principal in that account can exploit that trust. The attack could occur in several ways. A developer in the monitoring account might have legitimate IAM user credentials for developing and testing Lambda functions. If these credentials are leaked through a code repository, stolen from a laptop, or compromised through phishing, an attacker gains access to the monitoring account. The attacker can then use the AWS command line interface to assume roles in all workload accounts, potentially accessing sensitive production data or making unauthorized changes to resources. The proper remediation uses external IDs to ensure that only the specific Lambda function can assume the roles, not arbitrary principals in the monitoring account. Each workload account generates a unique external ID and configures it in their cross-account roles trust policy. The workload accounts then provide these external IDs to the operators of the monitoring account through a secure channel. The Lambda function's code is configured to use the appropriate external ID when assuming roles in different workload accounts. In practice, the Lambda function might retrieve external IDs from AWS Secrets Manager or AWS Systems Manager parameter store where they are stored encrypted. When the function needs to collect metrics from a specific workload account, it retrieves that account's external ID from the secret store, then makes the assume role API call including the external ID parameter. The workload account's IAM role validates both the account ID and the external ID before granting access. This implementation provides strong protection because even if an attacker compromises an IAM user in the monitoring account, they don't automatically have access to the external IDs stored in Secrets Manager. Access to Secrets Manager can be tightly controlled with resource-based policies and IAM policies that only allow the specific Lambda execution role to retrieve the secrets. The compromised user account cannot assume the cross-account roles without the external IDs, preventing the confused deputy attack. Additionally, you should implement least privilege on the Lambda execution role itself. The role should only have permissions to access the specific secrets it needs, invoke the specific APIs required for its function, and write logs to CloudWatch. It should not have broad IAM permissions that could be abused. The combination of external ID protection on cross-account roles and least privilege on the Lambda execution role creates multiple layers of security that an attacker must overcome. Automating external ID rotation. While external IDs, conclusion and security recommendations summary. The confused deputy problem represents a fundamental security challenge in cloud computing environments where cross-account access and service integrations are common. Throughout this presentation, we've explored the technical details of how this vulnerability works, why traditional IAM policies are insufficient to prevent it, and most importantly, how to effectively remediate the risk using AWS security controls. The external ID mechanism is your primary defense against confused deputy attacks. Every cross-account IAM role that trusts an external AWS account should include a condition block requiring a unique external ID. This shared secret ensures that only principals who know the external ID can assume the role, preventing unauthorized access even if an attacker compromises the trusted account. The external ID should be generated using cryptographically secure random number generators, be sufficiently long to resist brute force attacks, and be treated as a sensitive credential throughout its lifecycle. Defense in depth extends beyond just external IDs. Service control policies provide organizational guardrails that prevent dangerous operations even if a role is compromised. Resource-based policies add additional access controls at the resource level. Condition keys in IAM policies allow context-based restrictions on IP addresses, time of day, and other factors. Together, these controls create multiple layers of security that significantly reduce the risk of successful attacks and limit the damage if one layer is bypassed. Continuous monitoring and detection are critical components of a comprehensive security strategy. CloudTrail logging captures all assume role operations and subsequent API calls, providing the data needed for both real-time detection and forensic analysis. CloudWatch alarms enable automated detection of suspicious patterns like failed assumption attempts or anomalous access patterns. IAM Access Analyzer provides ongoing visibility into cross-account access configurations. AWS config rules ensure continuous compliance with your external ID requirements. These tools work together to provide both preventive and detective controls. Incident response planning ensures you can react effectively when attacks are detected. Document your incident response procedures in advance, including how to detect attacks, how to contain them by disabling or modifying roles, how to investigate the scope and impact of compromise, and how to recover normal operations. Practice these procedures through tabletop exercises so your team can respond quickly and effectively during actual incidents. Real-world scenarios. For example, S3 bucket access for backup services and Lambda cross-account execution illustrate how these principles apply in practice. The patterns we've discussed are applicable across many different AWS services and use cases. Whether you're granting access to third-party SaaS providers, implementing multi-account architectures, or building service integrations, the external ID mechanism and defense in-depth approach remain relevant and effective. Looking forward, security is an ongoing process rather than a one-time configuration. The investment in properly securing cross-account access pays dividends in reduced risk and increased confidence in your AWS security posture. Thank you for your attendance. Please consider subscribing to the channel and liking this video.